Welcome back to the Explainer, everyone. Grab those notes because today we're jumping straight into a really fascinating part of your software engineering course. We're doing a detailed deep dive into section 5.5, which is all about model-driven architecture. As your lecturer, I am super excited to walk you through this. We've got some incredible concepts to unpack, and then we're going to wrap things up with a big picture recap of all the crucial takeaways from Chapter 5, just to make absolutely sure you're geared up for those upcoming exams. Let's get right into it.
Okay, I want you to imagine something for a second. Think about the ultimate dream of software engineering. What if you could just sketch out your UML models, design the system, and then literally just hit a button and let a software tool automatically write the entire working program for you? I mean, no manual coding, zero syntax errors, just pure automated generation straight from your abstract designs. It sounds a bit like science fiction, right? Well, believe it or not, that exact dream is the core ambition behind the concept we're exploring today.
Here's our roadmap for today's Explainer. 1. An introduction to model-driven architecture. 2. The 3 levels of abstraction. 3. The translation process. 4. A reality check on MDA challenges. 5. A Chapter 5 summary recap. And finally, 6. Your exam focus. Section 1. Introduction to Model-Driven Architecture. Okay, let's dive into this first major topic. So, model-driven architecture, or MDA, is an approach that completely zeroes in on the design and implementation stages of building software. Instead of just jumping straight into the code, MDA relies heavily on creating models at different levels of abstraction to describe your system. By using a very specific subset of UML models, the main goal here is to eventually generate a working program with zero manual intervention. It's brilliant because it lets engineers think about the system at a super high level, which naturally reduces errors and speeds up the whole design process. But a quick heads up, a really common misconception students have is that MDA completely replaces human developers. As we'll see a bit later on, that's not exactly true.
Section 2. The 3 levels of abstraction. To actually turn this dream of automated software engineering into reality, the MDA method recommends creating 3 specific types of abstract system models.
First up, we have the Computation Independent Model, or CIM. You're also going to hear this called a domain model. The CIM is all about describing the most important high-level business concepts in plain, everyday English. It is purely focused on the business domain. So for example, if we were modeling a hospital system, this model would just talk about patient records, consultations, or security roles. Crucially, the CIM totally ignores computer jargon. It honestly couldn't care less about servers, databases, or programming languages. It's all business.
Moving down a step, we hit the second level, the Platform Independent Model, or PIM. This is where things start getting a bit more technical. We usually use UML models here to map out the system's static structure and dynamic behavior, basically how it responds to internal and external events. But as the name perfectly gives away, it is completely independent of the actual execution platform. The PIM does not care if the final program is going to run on Windows, a Mac, Java, or a .NET framework. It just defines how the system operates in theory.
Now, what's really interesting is how we bridge that gap into reality. The third level is the Platform-Specific Model, or PSM. This is a direct transformation of the PIM, but now it is officially tied down to a specific technology stack. In a real-world project, you'd actually probably have layers of PSMs. Your first PSM might adapt the model to a Java J2EE environment, and then a second one might tie it specifically to a certain SQL database. The PSM is exactly where our abstract, high-level design meets the cold, hard reality of specific hardware and software.
Section 3. The Translation Process. Let's look at the actual mechanics of how we get all the way from a high-level business concept down to a running program.
And this brilliantly illustrates that exact flow, straight out of Figure 5.19 in your textbook. We start all the way on the left with the computation-independent model. That gets translated into the platform-independent model. Next, a translator tool steps in, using specific domain guidelines to convert that into our platform-specific model. And then finally, another automated translator converts that PSM into actual executable code.
Let's break those exact steps down just a little bit more because there is a huge catch here. That very first step, translating the SIM to the PIM, usually needs a human being. Why? Because linking high-level abstract concepts is tricky. If you have a security SIM with a quote-unquote role and a hospital SIM with a staff member, it really takes a human who understands both of those environments to map them together correctly. But
Once you've got your PIM sorted out, the textbook notes that commercial software tools can automatically translate that PIM into multiple PSMs and then finally generate the executable code. So this brings us to the absolutely massive theoretical benefit of model-driven architecture. Imagine you've spent months building a huge system in Java, but 5 years down the line, you need to migrate the whole shebang to C#. In a traditional setup, you're rewriting that program. But with MDA, no way. You don't touch the code. You simply grab your existing platform-independent model, run it through a C# translator instead of the Java one, and boom, it automatically generates a brand new C# platform-specific model and the executable code. It makes adapting to new platforms incredibly fast.
Section 4. Reality Check MDA Challenges. Now, that all sounds absolutely amazing, right? But as your lecturer, it is my job to bring us back down to earth. If MDA is the ultimate dream, why hasn't it completely taken over the industry? Well, the textbook highlights a few major reality checks. First off, completely automated translation is rarely actually possible in practice. You're almost always going to have to roll up your sleeves and do some manual coding to get a system ready for production. Second, building custom translators for an organization's specific environment is incredibly expensive. Most companies don't just use vanilla Java. They have legacy databases, custom UI libraries, all sorts of things. Off-the-shelf tools just can't handle that, meaning the organization has to build their own custom translators, which costs a fortune. And finally, MDA clashes heavily with agile methods. Agile is all about iterative, fast coding and explicitly discourages massive upfront modeling, which happens to be the entire foundation of MDA.
Section 5, Chapter 5 Summary Recap. Let's move to and see how this builds into the bigger picture. We're going to zoom out for a holistic recap of system modeling to make sure you're ready for your exams.
Throughout this chapter, we've learned that using complementary models gives us these great abstract views of a system from different angles. We looked at context models, which are absolutely vital for defining the system boundary, basically drawing a line between what's inside the system and what's outside in the environment. We also dug into interaction models. We looked at use case diagrams for those high-level interactions with external actors, and sequence diagrams, which give us the detailed step-by-step communication happening between objects inside the system itself.
So, the crucial point is really understanding the core difference between the last two types of models. Structural models are your static architectural blueprints. Think of class diagrams. They show the organization of the system's design, totally frozen in time. Behavioral models, on the other hand, are all about the dynamic nature of a running system. We use activity diagrams to model dynamic data flow through various process steps, and state diagrams to map out how the system transitions from one state to another when an event happens.
Section 6. Exam Focus and Conclusion. Speaking directly to you as your lecturer right now, let's talk about what you absolutely need to know for your upcoming tests.
You absolutely must memorize the explicit definitions for the acronyms we cover today: CIM, PIM, and PSM. You need to be able to explain exactly what a computation-independent model, a platform-independent model, and a platform-specific model are. On top of that, you are almost guaranteed to be asked to explain the fundamental difference between structural and behavioral models. Just remember, structural is static, like an architectural blueprint. Behavioral is dynamic, showing the system actively processing data or reacting to events. And with that, Chapter 5 is complete. Honestly, huge congratulations to you. You have officially mastered the core concepts of system modeling. You know exactly how to abstract a system from multiple perspectives, and you completely grasp both the magic and the practical limitations of model-driven architecture. Up next in our course, we'll be transitioning into Chapter 6, which is all about architectural design. But before we wrap up this explainer, I want to leave you with one final thought to chew on. You now know how to draw the blueprints, and you know how to model the behavior. But as we step into architectural design next, how will you, as a future software engineer, actually bridge the gap between these high-level system models and the structural reality of a running program? Think about that, keep reviewing your notes, and I will see you in the next session.